Why are RNNs so unstable during training? Imagine trying to teach a robot to remember a long story. Sometimes it forgets the beginning or gets overwhelmed by the ending. That's similar to what happens when training recurrent neural networks. These models are designed to process sequences of data, like sentences or time series. They are used in language translation, speech recognition, and even generating text. But training them often feels like walking a tightrope. They can become unstable, making learning slow or even impossible. The main reason is something called gradients, which are signals that tell the model how to improve. When the model learns, it adjusts its internal settings, called weights, based on these signals. If the signals become too small, the model stops learning from earlier parts of the sequence. This is called vanishing gradients. It makes it hard for the model to remember long-term information, like the start of a story. On the flip side, if the signals become too large, called exploding gradients, the model's weights change too much in one step. This can cause wild swings in performance and make training unstable. These problems happen because of how RNNs process data step by step. Each step depends on the previous one, creating a feedback loop. If an error occurs early on, it can either fade away or grow bigger as it moves through the network. The choice of activation functions inside each neuron also matters. Functions like sigmoid and tanh can cause gradients to vanish because their outputs flatten out at high or low values. ReLU, another popular function, can sometimes lead to exploding gradients because it allows large outputs. The initial setup of the model's weights plays a role too. If weights start too large, gradients tend to explode. If they are too small, gradients tend to vanish. Longer sequences make these issues worse because the signals have more steps to grow or shrink. The structure of the RNN itself makes it tricky to learn long-term patterns. Errors can build up or disappear as they pass through each step, making training unpredictable. To fix these issues, researchers created techniques like gradient clipping. This limits how large the gradients can get, preventing explosions. Regularization adds penalties to large weights, helping keep the model stable. Better choices of activation functions and initial weights also help. More advanced models like long short-term memory networks and gated recurrent units were built to control what the network remembers and forgets, making training more stable. Understanding these challenges is important because they directly affect how well RNNs can perform in real-world tasks. If the model can't learn long-term dependencies reliably, the quality of generated text or predictions drops. This impacts applications like ChatGPT or image generators that depend on sequence understanding. From an ethical point of view, unstable training can lead to inconsistent or biased outputs. Knowing why RNNs are unstable helps developers build more reliable and fair AI systems. In essence, RNNs struggle during training mainly because of vanishing and exploding gradients. These issues stem from how the models process sequences, the math inside each neuron, and how they are initialized. Overcoming these problems allows RNNs to learn better, especially for tasks involving long sequences. Using improved architectures and training techniques makes these models more stable and useful for a variety of AI applications.